The last piece in the puzzle to talk about where the electrons are in the atom is to talk about the fact that we discovered that the electrons have a spin. The spin is a rotation on an axis, kind of like the Earth rotates on its axis. The spin can either be clockwise or counterclockwise, and we usually just generically call these up and down, just because it's easier to say up and down than clockwise and counterclockwise. And the reason why, or the reason how we discovered that the electrons had this spin is because you may recall the electrons are charged particles. We knew this at this point that we discovered the spin. And if there is a particle with a charge, if it spins, it generates a magnetic field. And we can actually measure the magnetic field generated by an electron. It's a really, really, really small magnetic field because electrons are really, really small. But our technology has gotten good enough that we have instrumentation sensitive enough that given the right set of circumstances, you see all these qualifiers, we can actually measure this magnetic field. Again, the spin will either be clockwise or counterclockwise. We'll call them up or down. Now, the wave function that governs each electron within an atom living in the orbitals basically has rules that apply to it mathematically, and one of the rules is that electron spins have to be paired if they're living in the same orbital. You cannot have two electrons spinning up in the same orbital. You cannot have two electrons spinning down in the same orbital. For that reason, in each orbital, only two electrons will fit, and they'll only fit with one spinning up and one spinning down. So now we know about the orbitals from the previous video, and now we know that because of their spin, only two electrons will fit into each orbital, and so now we can start building a picture of where the electrons are in the orbitals. The last piece, or the next piece, because there will probably be another last piece after this, but the next piece of the puzzle is to talk about the energies. It is commonly known that everybody wants to be at the lowest energy possible. And so as the electrons fill into the atom, and that's a little misleading because they don't really fill into it. We think of filling them into it, but they're there. But as the electrons fill into the atoms, they will fill in starting at the lowest energy possible, and then they'll go to higher energies only when they have to. So we need to know about the energies of the orbitals, and we've already talked about that a little bit. N equals 1 is down here at the lowest energy. If I think of this as an energy diagram, N equals 1 is down here at the lowest, N equals 2 is higher, N equals 3 is higher, N equals 4 is higher, and you may have noticed the way that I've drawn this is the levels are getting closer and closer together as I move up, and that's exactly what we find happening within the quantum mechanical mathematical formulas that describe the electrons in the atom. The higher and higher the energy level, the principal quantum number, the closer and closer the energy levels are. And because of that, within each energy level, within each shell, there are subshells. When n equals 1, the only subshell is S. When n equals 2, there is the S and the P subshell. When n equals 3, there is the S and the P and the D subshell. When n equals 4, there is the S, the P, the D, and the F, and I could go on and on and on. It turns out that the S and the P subshells for n equals 2 are not the same energy if there's more than one electron. Now, if there's only one electron, they're the same energy, which is why the hydrogen atom is so simple. But if there's more than one electron, these two subshells are at slightly different energies. The P subshell is a little higher in energy than the S. We still talk about them both being at the n equals 2 level, and the n equals 2 describes their energy, but they are technically at slightly different energies. When n equals 3, these three subshells, as long as there's more than one electron in the atom, they are at slightly different energies. The P is a little bit higher than the S, the D is higher than the P, and since these levels are getting closer and closer and closer together as I move up, they're starting to overlap up here. So the order that the electrons will fill into the energy levels becomes a little complicated because it's not just they're going to fill into n equals 1, then n equals 2, then n equals 3, then n equals 4, because these subshells start overlapping. We do have some pictures that show how this overlap works, and so we could use the picture to help us fill in electrons. All right, if we look at, let's look at this picture. All right, if we look at this picture, we see that n equals 1 is down here at the bottom. The n equals 2 energy level, you see how the 2s and the 2p are separated by a little bit of energy. For the n equals 3 shell, the principal shell, here are the 3 subshells, S, P, and D is high enough that the 4s is actually slightly lower. Here's the n equals 4 shell, and the 4s is a little bit lower than the 3d, and so what will happen in an atom is that the electrons will go into 4s before they go into 3d, and that complicates things a lot if you're just trying to learn, well, how do the electrons go into the atom? Then they'll go into the 4p, but before they go into 4d or 4f, they're going to start jumping into the n equals 5 shell because it's lower in energy. And so we need a way to think about how do these energies levels work without having to write that picture down or memorize that picture. In other words, how do the electrons fill into the orbitals, and we need an easy way to do that. And fortunately, we have an easy way to do that, and that is to look at the periodic table. If you look at the periodic table, it is arranged such that the atomic numbers go 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, etc. The atomic numbers are increasing as I move left to right, top to bottom. We talked about earlier in the chapter about the columns have similar chemical characteristics, and that's why we decide to start the new row. That's also why we have this gap here on the second and the third row, because we want to line up the elements such that the columns have similar chemical characteristics, chemical and physical properties. We call these groups or families. This tells us how to line up our electrons in an atom. Let me copy this picture into our paints so that we can draw on it. Alright, we don't need to see the symbols real well for what we're doing here. Basically what we're looking at is we are looking at filling in, each box is an electron. This is the hydrogen with 1 electron, helium is over here, helium's atomic number is 2, he has 2 electrons. Lithium has 3, then 4. Each atomic number is exactly the same number of electrons there are. With hydrogen, his electron is going to go into the lowest energy possible. The lowest energy orbital is the 1s orbital, and I'm going to put 1 electron in him, into that orbital, and this superscript 1 is for the 1 electron in the 1s orbital. We call this the electron configuration for hydrogen. It describes where the electron is in hydrogen, and when I say this out loud, I say 1s1. Helium has 2 electrons. Both electrons will fit into this 1s orbital as long as their spins are paired, as long as the spins are opposite, and so helium's electron configuration is 1s2. The 2 is for the 2 electrons that I'm putting in the 1s orbital. Once I get past helium, I am starting on my second row of the periodic table, and most periodic tables will even number this row number 2, and for lithium I am putting the next electron, the third electron, into the 2s orbital. So lithium's first 2 electrons are in 1s2, the same place as hydrogen and helium, but his third electron goes into the 2s orbital, and I only have 1 electron there. So lithium's electron configuration is 1s2, 2s1. Lithium's electron configuration builds on helium's. Helium's builds on hydrogen. We call this principle of building up on the one right before it Aufbau, a very good German word. I'm probably mispronouncing it. Aufbau. It means building up, and so the electron configurations build up one on top of the other. And after lithium, we have beryllium, and beryllium has 4 electrons. His first 3 electrons are exactly the same place lithium's are, and you'll notice this 2s orbital can hold a second electron, and so beryllium is 1s2, 2s2. There are his 4 electrons. When I get to boron, with 5 electrons. Boron jumps over here in the periodic table. His first 4 electrons are exactly where beryllium's are, but I can't put any more into the 2s orbital because only 2 electrons will fit into each orbital, and so I put boron's 5th electron in the next set of orbitals that have the next lowest energy, and those are the 2p orbitals. If you look back at that diagram we had a minute ago, I'll let you go look. If you look back at that diagram we had a minute ago, the 2p's come next in energy. He only needs to put 1 electron in there, and there's boron. Recall that the 2p orbitals were a set of 3. I can draw 3 lines here in a row to represent those 2p orbitals, and each orbital can hold 2 electrons, so I can put up to 6 electrons in this set of 2p orbitals, of which there are 3. Boron has 1 in the set of 2p, carbon would have a 2nd in the set of 2p, nitrogen would have a 3rd, oxygen would have a 4th, fluorine would have a 5th, and neon would have a 6th electron in that set of 2p orbitals, and so neon's electron configuration would be 1s2, 2s2, 2p6, and at that point I will have filled up the set of 2p, I will have filled up this subshell, and I need to start on the next orbital for the next atom that has another electron to put into it. You might notice that the periodic table, the row ends right here. That's because in this region of the periodic table, as we pass through these boxes, we will be putting electrons into p orbitals. This set, the 2 columns here at the beginning, have us putting electrons in the s orbitals. And what we're going to see when we get down here is that we're putting electrons into d orbitals. And so essentially the periodic table tells us what comes next. This is the 3rd row, so I'll start putting this electron in the 3s. This would be 3s1, 3s2. After 3s, I'd come over here to 3p1, 3p2, 3p3, 3p4, 3p5, 3p6. After I finish filling up 3p6, I don't jump to the 3ds. I come to the 4th row and put the next electron into 4s1, then 4s2. Now I'm going to fill in my d's. You'll notice the next box on the periodic table is not my 4p. My 4p is over here. This is my 3d. The 3's are 1 behind because of that overlap in energy. So 3d1 all the way through 3d10 with zinc, because there are 5 orbitals. A d subshell has 5 orbitals. Because of the electron spin, each orbital can hold 2 electrons. That means that 10 electrons can fit into a d subshell. There are 10 boxes across. That's where the 10 electrons go. Once I finish filling my 3d, then I'm back to my 4p. I finish filling my 4p here at the end of the row with krypton, and then the next thing I fill in is my 5s1, 5s2, and now I'll grab my 4. Remember that they're 1 behind, the 4d, 1 through 10. After the 4d10, now I'm going to be filling in my 5p's. These were my 4p's, these are my 5p's. Then I'll fill in my 6s's, and then a funny thing happens here. I jump down to this region of the periodic table. Let me make that a little clearer. After here, I jump down to this row. These are the F's. The F subshell shows up for the first time in the 4th shell, n equals 4. And if you count, there are 14 boxes across. There are 14 boxes because an F subshell has 7 orbitals. And 7 orbitals, each holding 2, means I can put 14 electrons in them. So here's where I fill in my 4 F's, here in the middle of the 5 D's, which come immediately after the 6 S's, but before the 6 P's. This is the 6 p's. This would be 7 p's. This would be 7 s's. This would be 5 f's when I need to jump down here. This was 4f, so this is 5f. So essentially following along on the periodic table, building one atom up past the one right before it, using Aufbau, that gives me my electron configurations.